post it online.
Are we supposed to write on the Google Doc?
You'll type in, yep, you'll type in your answers. So you'll have to make a copy of it. Yep, so you'll type it in, and then when we, right before we go, I'll remind you, but we'll just submit it into that assignment. All right, are we ready to go? So those of you here, like I said, you can stand. I'll try not to block the screen since I'm so tall. Just kidding. Not, really not. So the first one, you probably have seen before. So it's just a regular soda can. There's a little bit of water in the bottom. And then we obviously have it on the hot plate. Here we have a bucket of ice water. So you have to have cat-like speed and reflexes for this one. So we'll see how I do. And I'm very right-handed. So like, it's like backwards for this one. Okay, we ready? All right. 3, 2, 1, go. Okay. So take a second. Which 2 variables were affected? Oh. And then take a second, write down just your general observations. Say it again. Yeah, but then like from the camera angle, it's, yeah, so that was why I had to do it backwards, but it worked. We're good. Okay, so write down, so what 2 variables were affected? Temperature and pressure is one option. What's another option? Volume. Yeah, the volume of the can changed, right? So you could really have either one. I would stick with either temperature and volume or temperature and pressure and use either one of those for your explanation. But you could have, like, you could use either one to explain. All right, so take a second to write down your general observations, like what you saw and what happened. All right, so then I'm going to have the 3 of you discuss the explanation, so like what's happening to the temperature and why the molecules are moving like this and blah, blah, blah. And then I'm going to have the 4 of you discuss for your explanation. And then let's have the 3 of you guys chat. So sorry, I didn't and detail. And then let's have the 4 of you chat. And then let's have the 4 of you guys chat. So help each other out with your explanation. Here's the deal. I don't care if you're wrong. Okay, some of you have seen this before, some of you haven't, but like all I want you to do is start thinking about like, okay, well if this is happening to this, then why should this happen to this? Or what is, why did this happen? So I don't care if you're wrong, but I just want you to discuss like, okay, why did you see what you saw? Okay, ready to go. Aiden, you can jump in with these guys. You can jump in with these guys. You decide. Okay, all right, discuss the why. Ready to go. All right, so those of you at home we'll take a few minutes to discuss the why for each one, and then we'll kind of explain as a big group. So if you're curious, if your explanation is right, but so we will discuss. But like I said, I don't care if you're wrong. I just want you thinking about like how the molecules are changing and why you saw what you saw.
It's a good pressure.
All right, so who's got a good explanation? What did you guys say?
I said the molecules were really hot before entering the ice water, and then when it entered the ice water,
when you have heated molecules, right, they're moving, they want to take up as much space as possible, right? And the pressure didn't change because the lid was open, so those molecules could escape out of the top of the can. So you're right. So once you put those molecules in cold water, they go and kind of condense, like they get squished together because when they're colder, the molecules, they get closer together. They're not moving as fast. So were you explaining in terms of pressure or volume? Volume. Okay. So when the molecules go close together, what happens to the volume? Yeah, it decreases, right? So that could be one explanation, right? So the molecules were hot and moving all over the place, and then once you put them in the cold bath, they condensed and were squished together or compressed together, and that would decrease the volume. Who had pressure? Who talked about pressure? Okay, what did you guys say?
So the water molecules, I mean, when they were moving fast, they could be in cold water right away.
Mm-hmm. Yeah. So when we took the can and put it into the cold water bath, the temperature goes down. If the temperature goes down, what happens to the pressure? It goes down also, right? So with pressure, so we have atmospheric pressure, right? Like all the time pushing down on you. So pressure always wants to be equal. So if it's like pressure inside a container, the pressure inside the container wants to equal the pressure outside the container. That's why a lot of like aerosol cans and stuff like that will say like, keep in like a mild temperature, or like don't, decrease the temperature or increase the temperature past this amount. So even with like the air in your lungs, like the pressure inside wants to equal the pressure outside. So when we took the can and put it in the cold water, the pressure on the inside went down, and the pressure wants to be equal. So then if the pressure on the inside is less, the pressure from the outside crushes the can because it's trying to get that equilibrium. Yeah, nice work. All right, are we ready for demo number 2? Okay. So this, I used it last hour, so it's got some gross burnt stuff on it, but this is a hard-boiled egg. Okay, so I peeled it. So I hard-boiled egg and peeled it. And then this is just a regular flask. It's not a clean flask, but it's a regular flask. All right, so I'm going to light a wood splint. Okay, ready? Oh, it's taking a while. We'll see if it works. Whoop. There it goes. Kind of slow going. Oh boy. This is a really slow going one. Think I get stuck? Gonna get stuck. Okay. We'll try it again so it goes faster. But I want you to explain it first. So, okay, so chat with people around you. First of all, what 2 variables were affected? What did you see? And then why did you see what you saw? Okay, this one's a tough one. So take a guess. So like I said, the most important part of this is your thinking right now, even if you're wrong. Like it doesn't matter. Yeah, I know, it's so small rat and I've been here all day. turn and talk to your neighbors. Like, why did you see what you saw? What's changing? What's happening? Why did the egg go into the flask? Way to go. Like I said, this was tough.
Fire needs oxygen to burn, and it burns all the oxygen. Up to the temperature. Okay, fire needs oxygen to burn, and so once it burned all the oxygen, the pressure changed and the egg got sucked into the pressure. Yes, because it burned all the oxygen.
So one thing I should have reminded you, sorry, before your explanation, make sure you're talking about the gas and not the egg itself when you're talking about how things are changing. Because we're just talking about gases, right? All right, so what two variables were affected? So definitely pressure, right? Amount of gas wasn't affected only because we put the egg on top, so we trapped this set amount of gas in there. So it wasn't amount of gas. So what was another variable? Temperature, yeah. So temperature and pressure, okay? Volume was not affected because the size of the flask didn't change, right? The flask stayed the same. So temperature and pressure. Skylar, what did you guys talk about for an explanation? Rose, what did you guys talk about? I don't know what you guys talk about. For your explanation. You're all on the right track. And like I said, the important part, like, is not that you're right, like, you've never seen this before. The important part is you're thinking and processing and like trying to figure out what's happening. So when we put this wood splint in, the burning wood splint, what's happening to the temperature of the gas? It's rising, right? Because we added fire, right? So the fire is heating up those molecules. Well, when we put the egg on top and trapped the gas in, what happened to the flame? It went out. So when the flame went out, the temperature goes down, right? So it heated up those gas molecules, but then it went out, so the temperature dropped. If you have a drop in temperature, what happens to the pressure? It also goes down, right? Because they're directly related. As one goes down, the other goes down. So same thing with the, equalizing pressure. The pressure on the outside wants to equal the pressure on the inside. So if the pressure in here is less, that means the pressure outside is more, and it wants to try to compensate for that. So the outside pressure pushed the egg in to try to get that pressure to equalize again. So when the match went out, the gas in here, the temperature went down, which means the pressure on the inside went down. And since there was lower pressure on the inside, the outer pressure pushed the egg in. Okay, so now we have to get the egg out. And we can't break the flask. We can't run the egg. So what do I need to do to get the egg out? So what do I need to, like, what variable do I need to change? Okay, I could change the temperature. So what would you do temperature-wise? That would get the egg out. So if we want the egg to be pushed out, to what? Did you say heat it? Yeah. So if you blocked off this entrance, right? So if we put the egg where it's like blocking this gas and trapping the gas in here, I gotta show it like this, where it's trapping the gas in here. If you heat the gas, this pressure is going to increase, right? Because the gas molecules are going to spread out and it'll eventually push the egg out, right? So that's one way we could do it. What's another way using a different variable? So what if we change the amount of gas? So if we change the amount of gas, what would we have to do to get the pressure in here to build with amount of gas?
Make room for something to put gas into the closed off space. And
right?
Room for the egg.
So you'd have to get more gas in here, right? In order for the pressure to build and then to push the egg out, right? Okay. I'll be doing this in the other side. It's the grossest part of my day, guys. Ready? Oh, my egg is really struggling today. There we go. If you blow more air in, it is gross. Ew. If you blow more air in, then the pressure, as long as you have the egg blocking, you know, the pathway, once you blow more air in, then the egg kind of blocks that extra gas inside, and then the pressure pushes it out. This egg is really starting to smell now. Should we do it one more time, just faster? We'll see if we can get it to go faster. I'll add more fire. And then we'll do the last one. Woo, there we go. That's what happened first star. It's a little faster. All right. Might have to use a different one before third hour. Okay, last one. We'll just do 3 of them today. The other one, maybe we'll just watch as a video at some point in time. Okay, so this one is a candle in the bottom of this bowl. There's a little bit of water. I did color the water blue just so you could see the water a little better. So there is a little bit of water in the bottom. I don't know if you can see it. There it is. We just colored it blue so you can see it better. All right, so here's demo number 3. All right, you ready? This one takes a second. So this is just a plain flask. It'll take a second for you to see it. You can kind of see it. That's it. All right, so take a second. Explain your variables. Explain why you saw what you did. Last one. Ready, go. That's weird. Okay, so what two variables were affected? Temperature and pressure. Yep. So Gadit, what was your explanation? Okay, so it started out hot, right? So what happened to the flame? Okay, it went out. So when it went out, did the temperature, what happened to the temperature? Decreased. So decreased pressure, or sorry, decreased temperature means what for pressure? Decrease. So if we have less air pressure on the inside, what do we know about pressure on the outside? It's more, right? Because it wants to be, so if you have less on the inside, it's more on the outside and vice versa. So if this pressure, if the atmospheric pressure on the outside is greater, it's going to push down more on the pool of water on the outside, and then it's going to push water up into the flask, up into the column. Oops, that's not the one I want. Sorry, I'm getting my notes ready to go here. All right, so what I'll have you guys do once you have your third explanation down, I know there's a fourth demo listed on the assignment, but we're not going to worry about that one. So go ahead and in Schoology, go ahead and submit your document into that assignment for the gas law demonstrations. And that way it is done and finalized, and it's okay if your answers are wrong. I just want you to start thinking about how these variables relate to each other and why you see what you saw. So I'm not going to grade it for correctness. We're going to, just look at your explanation and see if you attempted. All right, did everybody get their assignment submitted? Okay. All right, sorry, this is kind of a long day. We're going to start notes now. So before we start notes, I'm going to have you guys stand up and with the same people that you've been talking to, tell them 3 things that you love that start with the letter X. So stand up, talk to your group. What are 3 things you love that start with the letter S? All right, I'm going to turn off this camera so we don't give you guys motion sickness, and then I'm going to set up my next part. All right, so you guys can, whoops. You guys can have a seat. We'll get started with notes. So grab out your notes packet. Those of you at home, you did get a link to the Jamboard. You don't need the link to the Jamboard. I just need it to write on it, so you don't actually need to access it. We'll work on it together as we go through our notes. So there's some parts that I'm going to write on and some parts that I don't need to. So we're trying all sorts of new things today. All right, so I think in your notes packet, this is on page 3. So it's got the table with the what does this law mean and the different gas laws. So we've already talked about like how pressure and volume affect each other, how temperature and pressure affect each other, blah, blah, blah. So these are actual like calculations where you have numbers that you're plugging in into the problem. So there's kind of 5 gas laws that we'll do this chapter before the test. Anyway, so we'll do 3 of them today. Some of them are like interrelated, so we'll talk about that next week. But, okay, so this is the table that you have in your notes. Just so you know, you do not have to memorize like that Boyle's law is this. Like you don't have to memorize the names of the laws. You would just have to know like how volume and pressure are related. So kind of like what we talked about with the demos. As volume goes up, pressure goes down. So these all come up at once. So we'll let you guys take some time to write them down. So Boyle's law relates volume and pressure. So as volume goes up, pressure goes down. So that's an inverse relationship. If it's inverse, the graph is going to be curved like this, just like the ones that you guys drew in your notebook from yesterday. And then the equation, so this is what we use for our practice problems, is P1 times V1 is equal to P2 times V2. And then Charles' law relates temperature and volume. So as temperature goes up, volume goes up. So that's a direct relationship. So as temperature increases, volume increases. So if it's direct, you divide. So V1 over T1 is equal to V2 over T2. A direct relationship is just a straight line going diagonal. This piece is important. So whenever you have temperature always has to be in the Kelvin scale. So you always have to change temperature to Kelvin. Oh, sorry. Spinning. Okay. And then the last one is Guy-Lussac's law. So Guy-Lussac's law relates temperature and pressure. So as temperature increases, pressure increases. And again, since they both go up, that's a direct relationship. So direct, you divide. Temperature is always on the bottom. With your calculations, temperature always has to be in Kelvin for this whole unit. And then since it's direct, again, you'll have that diagonal line that just goes diagonally up. So like I said, you don't have to remember which names go with which laws. You'll need to know like that. What does this law state? So, as volume does this, pressure does this. Or as temperature increases, volume increases. Those are the relationships that you'll have to know. All right, are we good with this slide? All right, so this is not, there's not a space for this in your notes. I apologize. I kind of forgot that I added this. So I don't know if you want to add them like up to the top of the little table or if you want to put them somewhere off to the side. Basically, all this is like when you read the story problem, you should know like if the number is in kPa, that's going to represent a pressure. Or if the unit is in milliliters, that's going to represent a volume. So it's just more like understanding what units go with which variable. So like I said, there's not a space to write it. If you can fit it up here, you can kind of make it 3 columns if you want to. But it's just mainly so we can understand what units go with which variable. So volume will either be in milliliters or liters. Pressure is in kPa, atm, or mmHg, which is millimeters of mercury. Temperature will either be in Celsius or Kelvin, but anytime you're plugging the number into the problem, it has to be in Kelvin. All right. Whoops. I'll give everybody a chance to finish up and then we'll switch our All right, we good? Okay. So I think that these now are the problems. So I'm going to switch my sharing here so I can write on it at the same time. Okay, so now I need to do this. All right, can you guys see that okay? It's the same examples that are in your notes, but this way I can like write on it. Those of you at home, do you see the example problems?
Yeah, we can see them.
Okay, thanks. Okay, so basically what you're going to do is read the problem, figure out what you know, what's given, and then figure out which equation to use. So if we had this problem, a given mass of air has a volume of, whoops, I got to find my writing tool here. Okay, a volume of 6 liters. So we already know that's a volume. So we're given a volume of 6 liters at 101 kPa. So kPa represents what? Pressure, right? So 101 kPa is pressure. And then we want to know what volume will it occupy. So we want to know a second volume at 25 kPa. So the pressure is changing to 25, whoops, kPa. And then it says if the temperature doesn't change. So the temperature is constant. I wonder how I can. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Already pinned. I wish this was bigger. All right, so if you have pressure and volume, which law will you use? Boyle's law, right? So the equation is P1 V1 is equal to P2 times V2. You do not have to memorize the equation either. And then you just plug in your numbers and solve. So P1 is 101 kPa. V1 is the 6 liters. That's equal to P2, which is 25 kPa, times V2, which we don't know. So then we just solve from here. So we would take the 101 times 6, which would give us, whoops, 606 for an answer. Here, let me add in the units quick. So kPa and liters both stay. And so that's equal to the 25 kPa times V2. So then we divide each side by a 25.0. And when we divide by 25, whoops, 0.0 kPa, that gets rid of the kPa unit. So then the only unit we have left is liters. So if you have 606 divided by 25, you get a volume of 24.24 in your calculator. All right, now guess what? This is super exciting. Guess what we get to do? Round to sig figs. Yes, they're never going away. They're always haunting you. Always, always. Oh. Okay, so 6.00 has how many sig figs? Not 2, but 3. Yep. Because the zeros are at the end of the number and after the decimal. So that has 3 sig figs. 101 has how many sig figs? 3. And then 25.0 has how many sig figs? 3. So this one is easy because they all have 3, right? Normally you go by the least number of sig figs. So we would keep the 2, we would keep the 4 and the 2. The last number would not cause the 2 to round up. So we would just round off to 24.2. And then what would our unit be? If it's volume, liters, yep. So 24.2 liters would be your final answer. All right, questions on that one? Okay, so here's the next one. So what information is given from number 2 in your notes? Brandon, what's one thing we know? All right, and kPa is? Yep, pressure, yep. So we know a pressure of 198, whoa. 198 kPa. Andrew, what else do we know from the second example? We know a pressure of 198. Do you see it in your notes? 27 degrees Celsius, which is a temperature. So what do we have to do to Celsius? We have to convert it to Kelvin. So before you plug in any numbers for Celsius, you always have to convert to Kelvin. So if we have Celsius, we add what number? 273. So if we have 27 plus 273, what does that give us? 300, yep. And with sig figs, when you add, it goes by decimal places. So 27 does not have any decimal places. 273 does not have any decimal places, which means it'll just be 300, but the decimal is going to go after the 0. So we'll keep practicing that with sig figs. Sophia, what else do we know from number 2? So P2 is 225 kPa. That's okay. And we want to know what's the temperature. So we want to know T2. So if we have pressure and temperature, we're going to use Guy-Lussac's law. So we have P1 over T1 is equal to P2 over T2. So then you just plug in your numbers and solve. So P1 is 198 kPa. T1 is our 300 Kelvin. And then P2 is our 225 kPa, and T2 is our question mark. So if these two are equal to each other, how can we solve? Cross multiply, right? You can do that. You can also solve for one side, set it equal to the other, but you can cross multiply. So if we take 198 times T2 is equal to 300 times 225. So 300 times 225 is 67,500. So then if we divide each side by 198, sorry, my writing is getting super small. If we divide it by 198, then we have to round to sig figs. So 198 has how many sig figs? 3. Remember, temperature we had to change, so we changed it to 300, but because we had to put the decimal point there, 300 also has 3 sig figs. And then 225 has how many sig figs? 3. So in 3 sig figs, what would our answer be? Well, we'd have to have it in 3 sig figs, but when you take the 67,500 divided by 198, what do we get? 341. And then since it's temperature, what's our unit? Kelvin. Yep. All right, questions on this one? All right, so I'm going to have you try the third and the final one on your own. So in your notes, the third one is listed there. So you have a sample of gas at 6.8 liters at 325 degrees Celsius. What will be the volume at 25 degrees Celsius if the pressure doesn't change? So write down what's given. Oh. And you want to know the second volume. All right, so whose law are we using for this one?
Charles. And what do we have to do temperature? We got to convert it to Kelvin. Okay, so take a second, plug in your numbers. Solve for your unknown. Oops. So you can cross multiply again. And then I'm going to give you a second to solve and check for sig figs, and then we'll double check your work. Oops. Okay, so turn to your neighbor and say, this is what I got for my answer. In sig figs, ready to go. What'd you get? I got this. Okay, answer should be 3.39. So we would use the temperature numbers for sig figs. Since it's a volume, what will the unit be? Liters. All right, how do we do? Okay. So here's the deal. Okay, we have like not very much time left, like 5 minutes. I fully intended, obviously having more than like 3 minutes of work time, sorry. So you were, you still have the quiz for today. However, I'll extend the deadline so you can take the quiz today. It might literally take you 3 minutes. It's 11 points, vocab. None of these calculations are on the quiz. Okay, so the calculations we'll do next week. So the quiz I'll extend to like Monday night. So you can take it anytime between now and Monday night. And then I'll remind you on Monday. But then also in your notebook, like if you know that you're going to have a busy week next week and you want to get ahead, you can work on like lesson 4 of your notebook. I think it's like slides 22 through 28 or something. But we'll also have like Monday, you'll have a lot of work time. We do have a few notes, but the notes on Monday will take like 7 minutes. So I promise that you'll have some work time on Monday. So don't stress about your notebook over the weekend. If you have a busy week next week, you can, try to get ahead, but don't feel like you have to. So we'll extend the quiz and, you can work on your notebook, but we'll have some flexibility next week too. So how's that sound? I don't want you to take a standardized test tomorrow and have a bunch of chem homework. Lame. Okay. All right. So those of you at home, thanks for sticking with us. You guys can head out unless you have questions. Thank you though.
Thank you.
All right. Thank you. All right. I got to stop my... Yowzers. So if you're behind in your notebook, like if you're super behind, then you might want to use some time over the weekend to catch up. But if you're on par, you're good. We'll get caught up next week. Yeah. You can keep it in Kelvin. So the only time you have to convert back is if the question specifically said, what is the temperature in Celsius? But if it's just asking for the temperature, then it's only in Kelvin. Yep. Okay. So next Thursday will be roll day. So I'll get that posted, but the test would be Friday. And then we've done. That'll be a week. But are you just glad you get it done? That was really? Oh gosh. Yeah, that'll be good. Alright, sorry today was kind of a lot of talking. So, thanks for. Hey, what do you have going on again?
A surprise birthday party.
Oh, yeah? For who?
My uncle.
Oh, nice. That'll be fun.